What we're going to do in the next few videos is look at various amplifier configurations in order to determine our small signal gain. So keep in mind, in the previous video we said we're ultimately concerned with our loop gain, but remember that our loop gain is just equal to our gain times our beta term. So even though right now we're going to be investigating our gain for a given amplifier configuration, we can easily convert this to a loop gain just by multiplying by that beta. So for this first video, we're going to be looking at a one-pole amplifier. And so what I have drawn here is a single stage common emitter amplifier. You'll notice we have these two coupling capacitors, CC1 and CC2. And so as you recall, the impedance for a capacitor is given by 1 divided by j omega c. And so what that means is that when omega is 0, our impedance is infinite. So these two capacitors are going to be blocking our DC. And so what that means is, if you look here in the middle, we have our voltage divider biasing, so we can bias our circuit without having to worry about our load on the right or our small signal input current on the left. At an appropriate frequency, our impedance for our capacitor is essentially negligible, so that becomes a short circuit. So what we can do if we are interested in our small signal gain is we need to look at our small signal equivalent circuit. So remember, a good way to start by doing is by identifying our base, our collector, and our emitter terminals. We draw the components that go between them, and then we can draw all of the external components. Keeping in mind that our CC1 and CC2 will be acting like shorts at our signal frequencies. So let's just come down here and say this is short at our signal frequency, and so depending on what your signal frequency is, you'll have to adjust those values. So here we see our small signal equivalent. So I've labeled the base, collector, and emitter with B, C, and E respectively. We have our diffusion resistance R pi. We have our dependent current source, this GM times V pi. I've neglected our output resistance between our collector and emitter, but we also have this term here, this C1. And so what this C1 is this is a combination of our base emitter junction capacitance and something called our Miller capacitance. And so basically what these are sort of non-ideal effects. So we've not looked at them before previously. If you want some more details on that, definitely look into chapter 7. And we're going to come back at the end of this unit and talk briefly about something related to this Miller capacitance again. But I at least want you to be familiar with the term. So what we want to do then is we want to analyze this circuit to find our small signal current gain. So we want to find the ratio of our output current, which is over here on the right, to our input current over here on the left. So let me go ahead and make some simplifications here so it's not as confusing as I'm writing my equations. So I'm going to go ahead and combine these resistors here. So we'll notice this is already R1 parallel with R2, and that's in parallel with R pi. So I'm going to go ahead and call this Rx, which is R1 parallel R2 parallel with our R pi. So that's going to make things a little bit easier. So let's start by getting an expression for our output current. So looking on the right side, we can do current division. So current division will give us our output current. So that's equal to the current going into the node, which is GM V pi. And then for our current division, we have the opposite current, which of the two in parallel. So in this case, RC divided by the two resistors in parallel. So RC plus RL. And so to be consistent with the notes, let's label this as equation 1. Okay, so ultimately, remember, we're looking for our gain, which is going to be our output current divided by our input current. So in this equation, we have our output current, but we want to be able to relate that to our input current. And so we can kind of see we're going to be able to do that through this V pi term, because our V pi is defined over here on the left side where our input current is. So let's now switch our attention to this left side. So we can say that our V pi is going to be equal to our input current times sort of this whole equivalent impedance that it's seen as it goes in. And so that impedance is going to be the resistance Rx in parallel with the impedance of that capacitor C1. So let's write that in a little more detail. So as you recall up here, I said our capacitor impedance is 1 over j omega c. Using the notation with just S, we can say that's 1 over SC, where S equals j omega. And that can make things a little simpler so we don't have so many terms flying around. So using our sort of simple equation for two components, two impedances in parallel, we have impedance of the first times impedance of the second divided by the sum of the two impedances, so Rx plus 1 over S times C1. And so this is of course a little messy to look at, so let's simplify it a little bit by multiplying numerator and denominator by S times C1. And so that's going to clean that up a little bit, and we're going to be left with V pi is equal to I sub I times Rx in the numerator divided by 1 plus S Rx C1. Okay, and again, to be consistent with our notes, let's call this 2. And so what we're going to want to do now is we're going to want to take this expression for V pi from 2, and we're going to substitute it into expression 1 up here. And so ultimately that's going to give us our I out and our I in the same equation. And then we can solve for our gain as Gm times Rx times Rc divided by RL plus Rc times this 1 divided by 1 plus SRX C1 term. Okay, and again, to be consistent with the notes, let's call this equation 3. So now looking at equation 3, notice we've said that our loop gain is a complex value, and of course we see that's true for this gain as well because we have this S term. So with any complex value, we're going to have a magnitude and phase. So we can rewrite with our magnitude and phase information. So actually before we go to that, let me simplify this a little bit. So let's rewrite this as AI is equal to A sub I0 divided by 1 plus j times omega over omega 1. And now, so why do I want to do that? Well, and let me clean this up. So this is A sub I0. So our A sub I0 in this case is going to be equal to the Gm Rx times Rc over RL plus Rc. And so what this is our low frequency gain. So this is sort of our default gain at lower frequencies. As our frequencies increase, we're going to deviate from that. That's going to be made more clear as we look at the Bode plots here in a second. And our omega 1 we also want to define. So our omega 1, by comparing 3 with this circled expression here, we can see that our omega 1 is going to be 1 divided by Rx C1. And if you recall from ENG 301, this was sort of a basic form we looked at in Bode plots, and this omega 1 in this case corresponds to our upper 3 dB frequency. So our upper 3 dB frequency, which as you also might recall has a lot of names, our corner frequency, our break-off frequency, any number of names that we can call that. So to sort of show explicitly how we could rewrite this then, in terms of our magnitude and phase, we could say that this AI is equal to our magnitude, which is going to be our low frequency gain, divided by, so in the denominator there we have sort of a complex number in rectangular form, so A plus JB. So to get the magnitude, we do square root of A squared plus B squared. So we get this. And now for our phase in our numerator is 0. So we're going to have 0 minus the phase of the denominator. So 0 minus is the same as just say negative. And now for A plus JB, the phase angle is going to be inverse tangent of B over A. So we have negative inverse tangent of omega divided by omega 1. And of course that's divided by 1, which doesn't change the form at all. So with all of this information here, what we can do is we can create Bode plots to better represent what this looks like. So of course our Bode plots are going to have sort of two pieces of information. We're going to have gain or magnitude information and then phase information. So our magnitude of this small signal current gain typically is going to be plotted in decibels, and that's as a function of frequency, which is on a log scale. And we also have information for our phase, and again that's also with respect to frequency, omega. So let's look at our gain first. So our key frequency we set up here is this corner frequency or 3 dB frequency omega 1. So our omega 1, if we're doing sort of our linear approximation with our Bode plot, here if this is our magnitude, we're going to have, again if we want to convert this to dBs, we're going to have 20 times the log of this AI0. And that's going to be constant at that value until we reach this corner frequency, at which point we're going to be dropping off at negative 20 dB per decade. So here our slope is negative 20 dB per decade. Okay, and just to be clear, this sort of corner frequency is related to our omega 1 there. So now for our frequency, so remember we have a log scale for our frequency. So if I have omega 1 there, I have a tenth of omega 1 here and 10 times omega 1 here, which are evenly spaced on this log scale. And so what we've seen previously in another class is if we're plotting the phase information for this single pole, we can use a piecewise linear model. And we can say our two sort of key frequencies here are going to be negative 45 degrees and negative 90 degrees. And so let me just draw some lines out here that are going to help with this. And so basically what our linear approximation says is that at our corner frequency of omega 1, our phase is going to be negative 45 degrees. And so that's actually true regardless. So our linear approximation then is we say if we're less than a tenth of our corner frequency, our phase contribution from this is just 0. And if we're greater than 10 times our corner frequency, our phase contribution is negative 90. So we just use a straight line to connect those, and that's going to be our linear approximation. So of course we have a negative 45 degree per decade slope here. And so we're going to move on, so we're not going to spend too much time talking about this because we want to move on to look at our 2-pole and ultimately our 3-pole amplifier. But what we can see is, think back sort of to get an idea of where we're going. We're looking at the magnitude of our loop gain and the phase of our loop gain, and we said for a certain phase, a negative 180 degree, depending on what the magnitude of our loop gain is, our circuit is either going to be stable or unstable. So we can see that if we're not able to get to that negative 180 degrees, we shouldn't have issues with being unstable. So in the next 2 videos, we're going to look at more complicated amplifiers, and we're going to see that this phase angle actually drops further, and then we're going to come back and quantify our degrees of stability for various systems.